Okay, this lesson talks about simple harmonic motion, but in specifics. So SHM, but we're going to look at specific examples. But before we do that, I just need to remind you of what we ended up with at the end of the last lesson, the lesson 1 on this, and lots of maths that was gone through. But the real idea that I wanted to draw from that is the idea that acceleration is equal to minus omega squared x. That's the conclusion we drew. In that, we have a definition for simple harmonic motion. The acceleration is directly proportional to the displacement, and it's a restorative acceleration, and this is the constant proportionality omega squared. And we gained that because we started, the outset was that the displacement was in the form of amplitude cosine omega t plus epsilon. And when we double differentiated it, we double differentiated this, and we realised that the difference in the functions before and after was just omega squared. Okay, so now we've got a few examples to take a look at. The first of which is going to be a mass on a spring. And there's different setups of the mass on spring. I'm going to show you the easiest one first. Let's imagine it's working sideways. And the reason why it's working sideways is because we're going to take out gravity out of this situation. We have m, and we have a spring constant of k. And if we displace said object by a distance of x, what happens then? Well, I'm sure you'll appreciate that we have a force, a restorative force that starts to act, and it is of the value of kx, just as Hooke's law would predict. So there's our setup. Let's go back to the equation. We know that the force is kx. We know acceleration is equal to F over m. So therefore kx over m. And that gives me, and of course it's a restorative force, so minus in there, minus k over m x. Acceleration is minus k over mx. It's a simple harmonic oscillator. Oops. That's not what I was meant to draw, but it's a simple harmonic oscillator, a mass on a spring, and that's defined by this equation because the acceleration is directly proportional to the displacement. It's restorative. Here is the specific constant proportionality I have in this instance. So we can equate the two. We can say that this is equal to minus omega squared, because I've taken this identity. And to make life easier, add both sides, positive. And I also know that omega is 2 pi over t. So now I can relate the time period to this system. Let's move this around a little bit, just to be absolutely robust. We can say k over m square rooted gives me 2 pi over t. I'll invert the whole thing. Over 2 pi is root m over k. And so therefore finally I'm just going to move the multiplying factor of 2 pi up to there. There is my time period for a mass on a spring. Remember, there's no dependence on amplitude here. It doesn't matter how far this is moved, it will still have the same time period. The time period is affected by m, because for the same restoring force, if you have a heavier mass, it's less likely to move, and it's got more inertia, and how hard the spring is pulling. Okay, and a few manipulations of that which you could work through. We could say F, of course, is 1 over the time period, which gives us 1 over 2 pi, root k over m, and other forms of the like. There may be a few considerations to bear in mind when we're dealing with this, and that being that, of course, with springs, you can have more than one. And you might find them in a parallel combination or a series combination. Now, in parallel, remember, the total spring constant is the addition of each individual spring constant, whereas in a series combination, the total is the addition of the reciprocal, just like capacitors, or the opposite to resistors, etc., etc. And then you just substitute that into this part, into the k that we're using here, and the equations will drop out. I think it's also probably worth mentioning here that this omega in simple harmonic terms is called the pulsant. An odd term, I don't want you to get confused as to what it is. It's omega, in other words. So bear that in mind. Now, there's also another way in which the springs might be put together, and that would be if you cut a spring. Now, if you cut a spring, the spring constant will increase by the amount. So let's imagine you halve it, then the spring constant will double. So bear that in mind in case you come across an example. I've only seen one ever that does that. And the other one that's a bit strange because it's slightly counterintuitive, and that being that if you've got your mass that's suspended between two springs, you might imagine that's a series setup. But double check it might not be, because some springs, of course, work in both compression and extension. Now, if they work in both, then putting one on both sides will actually double the spring constant. So this system will be twice the spring constant if these springs are acting in both compression and extension, whereas in the classroom you've probably only seen them acting in extension. I think we're probably ready to try an example. Okay, now let's look at the mass on a spring, and we have 50 Newton meters for the spring constant. We have a, I'm just reminding myself of the mass, 0.5 kilogram mass, and we're going to displace it by 5 centimeters. Now, what's the equation of that subsequent motion using this form here? Okay, if you think you know the answer, hit pause. Otherwise, here comes the answer. So what we need to work out, the amplitude. Well, that's quite straightforward. That's going to be 5. And we need to try and work out omega. Now, omega, we know from back up here that omega squared is equal to k over m. So therefore, omega itself is going to be root k of m. So we've got the equation that we need there in order to work that out. Omega, in this instance, is equal to root k over m, which is 50 divided by 0.5 square rooted, which is the same as root 100, which gives us 10 radians per second. So our form is, we have 5 in centimetres cosine 10t. And we can work out any subsequent time period of that. For any subsequent period of time, we can work out the oscillations. Okay. And let me talk a little bit more, because another point point to make here is a vertical mass on a spring, which is a bit of a unique case, because you might say to yourself, I don't think this is a simple harmonic oscillator, because we've got gravity acting on it, and we've got our force, which is kx. So you could say to yourself, well, I think that the force, that would be the spring constant, has got to equal mg equilibrium, which you'd be right in saying. Now let's imagine we move off equilibrium. Let's imagine we moved a little bit higher. What takes place there? Well, the restoring force is going to be the force, which is the new force coming from the spring, which is going to be F0, or F0 there, minus kx. We already know, oh, sorry, that's right. So F0 minus kx, the difference in forces, minus mg, because mg still exists. So whatever the force F0 exerts here, as it moves up slightly, so there'll be a difference in F0, a reduction in F0, because it's moving up a bit, but we've still got the mg acting there. Indeed, if we add a little substitution, we know that F0 is mg minus kx minus mg. And these two drop out, so the resultant force is equal to minus kx. And therefore the acceleration equals to minus k over mx. Once again, it is a simple harmonic oscillator. I hope you can see that through. It's a technicality, but often some people go, oh, hold on a minute, F resultant is kx minus mg. Oh, no, it's not SHM. But what we're not taking into account there is what the F0 is at equilibrium, and therefore this part, in effect, just drops out. I'm not sure if I've been clear enough there, but don't get confused. Mass on a spring vertically, so long as you're not going past a point of elastic limit, or the spring is not compressing so far it's no longer causing a force, it is still a simple harmonic oscillator, which is well worth noting. One last example, shall we? Let's look at a spring constant of 30 Newton meters and a 300 gram and just work out some factors for this. So another example. Another mass on a spring. Got 300 Newton meters. And we will have a mass of, sorry, it's 30 Newton meters, that's right, 30 Newton meters. And we're going to have a mass of 0.3 kilograms. Let's work out what the pulsant is. Let's write that a bit better. Then we can work out the frequency, and then we can work out the time period. Okay, if you think you know how to do it, hit pause. Otherwise, here comes the answer. Well, very simply, K over M, we've done it before, so we can jump straight into that solution. 30 over 0.3 gives me root 100, just like before, which gives me 10 radians per second. Of course, the frequency is going to be omega over 2 pi, which gives me 10 divided by 2 pi, 5 over pi, which gives me an answer of about 26.5, hold on, let me just make doubly sure, 1.59, that's right, hertz, or per second. The time period is 1 over the frequency, 1 over 1.59, which gives us 0.69 seconds as a time period. Wonderful. I think we've really we've explained that one in all its possible variations. Right, here comes the next one, which is a pendulum. We have a mass and a force mg. We have it suspended. It's going through a certain number of angles, and there'll be a tension created in the rope. Now, let's try and work out what is this restoring force F acting back. Well, we need to resolve T in terms of its vertical components and its horizontal components, and then we will find out what F is. So what is the resolution? T cos of theta, if this is theta as well, this is a factor as T cos of theta, and this one is going to be T sine of theta. So let's write those in. T cos theta is going to equal mg. So therefore T is mg divided by cos of theta. We know F is T sine theta, which gives us mg sine theta, substituting now, mg sine theta over cos theta. Of course, I'm looking for the acceleration, so divide that by m, divide this by m, and that side by m, cancels, giving me g and tan theta. You know, sine theta over cos theta is tan theta. Okay, nearly there. Now, take a look at this triangle we're dealing with here. We have length L, and we have x, the displacement. Now we know that sine theta is approximately equal to tan theta, which we know to be opposite over hypotenuse, should I say. And that's for small angles. When we use small angles, it's anything less than or equal to about 11.5 degrees. So my last step can say that if this equals gx over L, acceleration equals g over L over L x, and because it's obviously a restoring force, I should be rigorous. And there is my analogy with the harmonic oscillator. So, just like before, we write down omega squared is g over L, which is the same as 2 pi over t squared. Let's do some rearrangements. To the square root g over L, 2 pi over t, and then I'll just invert them. T equals 2 pi over g over L, which is the same as multiplying the reciprocal L over g. There is my equation for the time period of a pendulum. Right. Maybe we need some examples of that. Let's take the example of a clock. Let's say, obviously we know that clocks time 1 second each swing. So therefore we know the time period is 2 seconds, because obviously we need to go from this position to there, back again. So therefore, what is the length required in order to create that? Okay, if you think you know the answer here, pause, otherwise here comes the solution. We have T is, let's start from the basics, and we're going to have T over 2 pi, Square that up gives me L over G. So therefore G T over 2 pi squared equals L, which is 9.81 by 4 over 4 pi squared. That's 9.81 over pi squared, which is 0.99 meters, approximately. That's the reason the clocks are as tall as they are. Wonderful. Now, of course, we can adapt this to any system we want, because remember, we always are looking for the form of the equation x is a cos omega t minus or plus epsilon. This often we can ignore. But if I were to want to write that previous equation, the previous setup in this form, it would be, let's imagine I've displaced it by a certain amplitude, cos, and omega would be, in this instance, 2 pi over t, t being 2 seconds, which leaves me with pi t. Imagining I've started from the edge as a maximum display as 0. So this is when t equals 0. Therefore, epsilon equals 0, because I've got a maximum displacement at my start point. Okay, let's try another example, another system. Let's try a cantilever. We have a weight acting on this system, and there'll be a natural displacement for that weight. We're also then going to move it down by a certain amount in order for it to start oscillating. Clamped, clamped. Now in this instance, you're just going to be told information, so you have to start to work out what's going on. For instance, we're told that its displacement standard position is 1.5 centimeters and it's 200 grams. We know it behaves like a spring. So therefore, can we work out an equation for how this works? Well, if it's spring-like, it's going to have a spring constant K, which is going to be the force exerted divided by the extension that's found, just like it's just a Hooke's law problem. The force is mg over the displacement, so therefore we've got 0.2, careful we've moved this from grams into kilograms, and 9.81, and we divide that by the 1.5 centimetres. Okay, that gives us something like 131 newtons per metre as our constant. Nice. Now what does omega equal therefore? Omega is going to equal root k over m. It's spring-like, that's the key. Which gives us root 131 over 0.2 square rooted, which is 25.6 radians per second. And now we're nearly there. Remember, x is a cos omega t, and we're hoping we're starting from a point which means epsilon is 0. Or should I just write that in to show you? We're going to say that's 0 because we're going to start from a maximum displacement here, t equals 0. Now that gives me a displacement is 1 centimetre. I should have mentioned that before, but now we've got it. 1 cos 25.6 t, or if you like, cos 25.6 t is the equation for this system. Okay. I hope that all makes sense.